Hey everyone, my name's Sam, and today we're going to talk about NWP and how it's used in wind resource forecasting and assessment. And I thought it would be appropriate for my first slide to include three frames from a WRF limited area model of the US for the day that this presentation is due, which is the 6th. And it's showing the wind conditions for the US over a 6-hour period. And yeah, let me know um, if this is accurate after you watch this. Excuse me. Um, So where did NWP come from? Well, in the early 20th century, there's this Norwegian physicist named Wilhelm Bjerknes, and he surmised that you could predict the atmosphere and how it changes with basic physical laws and equations. And so about 20 years later, Louis Fry Richardson, this Englishman, decided to try this. And he basically tried to make a 6-hour weather prediction over two geographic points in Europe. And it took him about 6 weeks to calculate using Bjerknes equations. And this was pretty damn slow. So the next development came in 1946, and there's this genius Hungarian physicist named John von Neumann, who founded the Princeton Meteorological Program. And he decided to try Bjerknes equations again, but this time with the help of computers. And using one of the first computers, the ENIAC, programmed by mostly women, which I thought was pretty interesting. He was able to do these equations super fast, and he started producing these reliable weather forecasts. Um, and so over time, Moore's law basically states that transistors can get smaller and smaller, computing power can increase, computers get smaller, and so NWP just took off as computers did too, and they got a lot better. So a couple things to address here. I included a couple of pictures, but there's a picture of von Neumann sitting with the funny physicist Richard Feynman. If you haven't read his book, you should. Um, and Stanislaw Ulam, who invented the Monte Carlo method in mathematics. So a couple of smart dudes sitting on that bench, and there's this one quote by Feynman. Von Neumann gave me an interesting idea that you don't have to be responsible for the world that you're in. So I've developed a very powerful sense of social irresponsibility. And I thought that was kind of a funny quote because von Neumann is basically one of the fathers of NWP, which is, I think, a huge socially responsible system that we have because it saves a lot of people, and points to anyone that can predict who, or sorry, not predict, but who can guess who that is in the bottom left picture, the skinny guy next to von Neumann. Okay, so transistors have been getting smaller and smaller, and now, skipped a couple steps, we are here at WRF, which is the weather research and forecasting model. And WRF basically runs on these two dynamical cores, and this basically means that basically these two cores rely on a different set of physical assumptions. One's non-hydrostatic and one's hydrostatic. And this is just preferred for reasons that I'm not sure of. So AWR is mainly used by NCAR, and it's used as a research tool and for experimental real-time forecasting, convection forecasts, high-resolution hurricane simulations, and developing new ensemble technology. NMM is used mainly by NOAA and the National Center for Environmental Protection as a hurricane forecasting tool. And I found this one paper from 2011 where these researchers wanted to see if they could predict the hurricane path of Hurricane Katrina using a couple of these cores and methods. And I thought it was interesting that NMM on the right graphic was the worst performing one and did not predict Hurricane Katrina properly with the initial conditions. And on the left is the actual hurricane path. So I thought that was kind of interesting. Not related to wind, but related to the computing. Okay, so let's take a step back from WRF and fill in some of the gaps here. So some of the more basic NWP models used for wind are mass-consistent models, Jackson-Hunt models, and computational flow dynamic models, or CFD. They work off of universal physics equations like Bjerknes equations in the early 20th century, and they probably use some of Bjerknes equations too. But that's a basic idea. They start with an atmospheric state, and they basically calculate the change in the atmospheric state over time using a bunch of variables. And this is a very basic equation I included in the top right. One of these examples of a Jackson-Hunt model is in the middle, and you can probably guess which one it is based on the little cartoon. It's WASP. But it's a step above these mass-consistent models, and they're more advanced. They use more parameters, but they cannot deal with complex terrain at all. And this is going off of Brouwer's chapter on NWP. And he quotes that complex terrain is defined as a terrain where the slope exceeds 30% over a significant portion of the area. So if an area is more than 30% slopey, then WASP is going to be basically useless. So basically the next step was using models in 3D space with computational fluid dynamics. And they're a bit more complicated. They still use these simple fluid dynamics equations and stuff. But this is also from Brouwer. They found that I think it was 13 to 17% of CSD results were not accurate, and they overestimated wind resources, I believe. So we don't use them a whole lot. And in the bottom left, like all of these models on this slide would be perfect if we lived in the super flat Minecraft world, but sadly we do not live in this perfect perfect square flat Minecraft world. So we need to use WRF. So like I just mentioned, WRF is really good at utilizing a bunch of really complex parameters and parameterization schemes like cloud microphysics, soil moisture, solar radiation, and convection. But yeah, the basis of all of these parameters is really strong observational data and measurements from wind resource assessments. And this opportunity was too great to pass up, or to not pass up. I'd like to apologize to my girlfriend because she was one of the authors on this, and it just came out today, April 6th. But it was this wind resource assessment campaign by Livermore in California, and it's called the Hill Flows Project. And they're trying to see if the vertical wind profile, I believe, is different in this hilly terrain in Altamont Pass by Livermore. And so they had these two sites where they took LiDAR measurements and they measured the vertical wind profile. And they found that the wind resources were actually greater, less than 80 meters, less than hub height in this hilly terrain. And I included a couple graphs there. I think the bottom graph shows that the wind resources are much greater below 80 meters in all those graphs. So yeah, that's really important if you're trying to use this complicated WRF model for your wind resource projections and predictions, because this is this phenomena that perhaps the model wouldn't pick up on its own. So it requires this observational data. So yeah. Okay, so the last point I'd like to touch on is, okay, so WRF is kind of the best NWP that we have out there, but the problem is it's very expensive. It takes a lot of computing power to run. I saw this figure on the NCAR website that a 10-kilometer resolution WRF model costs 27 times more than a 30-kilometer resolution model. And these are grid resolution. So each grid square is this kilometer resolution. And the 1 kilometer resolution globally costs 1,000 times more than the 10-kilometer resolution. So I'm not exactly sure if that's right, but I thought that was kind of a crazy figure. So what researchers do to combat this is this thing called nesting, and it makes the model more efficient. It doesn't have to run a whole global model every time it wants to run a localized model, like I included in the first slide of the US. And the way that it does this is in order to generate the boundary conditions for the local area model that it wants, basically the edge conditions, it runs basically a parent WRF simulation in a larger area than the target model at a pretty coarse resolution, and that just provides this coarse boundary layer data to the inner square, and that saves on a whole lot of computing power, a whole lot of money, and it will make a wind resource assessment a whole lot cheaper. And yeah, that was my presentation. Here are the scientific points that I tried to cover in the presentation, and here are my sources. And thank you for listening.